Hello everyone. In this video, we will discuss about casting defects. An unsuccessful casting results in considerable trouble and loss of time. In almost all the instances, these defects can be avoided if one follows the proper protocol and principles. So, the casting defects are attributed to the carelessness or ignorance of the operator. Unless every step in the casting operation is handled properly, the cast restoration may not fit the prepared tooth with desired accuracy. So, they are broadly categorized as distortion, surface roughness and irregularities, porosity, and incomplete casting. So, first we will discuss about distortion. Any marked distortion of the casting is probably related to a distortion of the wax pattern. So, how do we minimize this? In order to avoid these, we have to do the proper manipulation of the wax and proper handling of the wax pattern. The thickness of the wax pattern, the type of the wax, and the configuration of the pattern can produce distortion. Unquestionably, some distortion of the wax pattern occurs as the investment hardens. At the time, the setting and hygroscopic expansion of the investment will produce a non-uniform expansion of the walls of the pattern, and it will cause a non-uniform outward movement of the proximal walls of the pattern. The gingival walls will exert an outward movement, whereas the occlusal surface resists this non-uniform outward movement. The surface roughness and surface irregularities. What is surface roughness? These are the finely spaced surface imperfections whose height, width and direction establishes the predominant surface pattern. That is, they are present throughout the casting. Alright, and the surface irregularities are the isolated imperfections like that of the nodules or the ridges that do not characterize the total surface area. So, the basic difference here is that the surface irregularities are not present throughout the casting, but they are present in a particular area only. Alright, the excessive roughness or irregularities of the casting further necessitate the additional finishing and polishing of the casting, and if the surface irregularities are present in the critical areas, obviously we need to redo the whole casting. So what all factors causes the surface roughness and irregularities? The water powder ratio. The higher the water powder ratio, the increased surface roughness of the mold. And if the water powder ratio is less, in that case the investment material is quite denser, and during vacuum investing the air cannot escape out, and that may cause the air voids that will be further reflected into the casting as in the form of the surface irregularities. Next is the composition of the investment. The coarse silica causes a rough surface. Prolonged heating and rapid heating rates also leads to the investment degradation and flaking of the investment when water or steam pours into the mold. Overheating causes a reaction between the alloy and the casting investment. Too high temperature of the molten alloy before casting, the surface, in that case the surface of the investment is likely to get attacked, and there will be the roughening of the mold wall which will be reflected into the casting also. Coming on to the foreign bodies. When foreign substances get into the mold, a surface roughness may be produced. Say for example, a rough crucible former with investment clinging to it. It may roughen the investment on its removal so that the bits of the investment are carried into the mold with the molten alloy. So foreign body in the form of dirt in the wax pattern, pieces of the investment or bits of carbon flux from a flux is not desirable at all. Usually contamination not only result in roughness but also sharp, well-defined deficiencies can be seen in the casting. Now the impact of the molten alloy. The direction of the sprue former is of very important, because the direction of the sprue former should be such that when the molten alloy it should not directly hit onto the weak portion of the mold surface. Otherwise, it may fracture or abrade the mold surface. Sometimes the abraded area is smooth and it is not detected in the casting, but sometimes it appears as a raised surface in the casting surface. Next is the pattern position. If several patterns are to be invested in the same ring, they should not be placed too close together. At least 3 mm of space should be there in between them, because the expansion of the wax is much greater than that of the investment, and this may cause breakdown or cracking of the investment if spacing between them is less than that of the 3 mm. Coming on to the air voids. So the small nodules on a casting are caused by the air bubbles that become attached to the pattern during or subsequent to investing procedure. Even a minute nodules can limit the seating of a casting to a considerable degree, and the large one, that are those, especially those situated on the critical margins, necessitate remaking of the restoration. So in that case, what to do? The best method is to use a vacuum investing technique. Use of a mechanical mixture with vibration both before and after mixing should be practiced. And the use of the wetting agent should be applied in thin films. It's not like that we are applying. No, we have to apply a thin film only, and after that we have to air dry it. Otherwise, the wetting agent may dilute the investment. The careful coating of the wax pattern with the investment should be done. Next is the water film. We all know that the wax is repellent to water. If the investment become separated from the wax pattern in some manner, a water film, this is the blue color here, may form regularly over the surface, and this is manifested as ridges or veins on the surface of the casting. Alright, so here a wetting agent is helpful obviously, but what causes this water films? If the pattern is moved slightly, jarred or vibrated after investing, in those cases, and if the painting procedure does not result in an intimate contact of the investment, and also the water powder ratio is too high. Next is the fins. These are caused by the cracks in the investment filled with molten metal. This increases the time required to finish a casting. If the defect occurs in critical area, need to recast. Causes too rapid heating rates, radial cracks due to non-uniform heating, high water powder ratio, weak investment. It will cause it more prone to cracking, and premature heating when the mold is still wet. The excessive casting pressure, it will lead to metal impact, and that will cause further fracture. So what precaution we have to follow? Avoid prolonged and rapid heating of the mold, use of correct water powder ratio, use of adequate casting pressure, and careful handling of the mold. Now coming on to porosity. So where is the porosity most common likely to occur? We have both internal and external porosity. External present on the external surface of the casting, internal present on the internal surface. It weakens the casting, and if it extends to the surface, it will cause a discoloration, and if it is severe, it can cause leakage at the tooth restoration interface. That is, it may cause secondary caries development. So coming on to the classification of the porosity, they are classified as into further two categories, that is the solidification defect. Under this we have the localized shrinkage porosity, microporosity, suckback porosity, and the trapped gases. Here we have the pinhole porosity, gas incursion porosity, and the subsurface and backpressure porosity. So coming on to the localized shrinkage porosity. So basically what happens, whenever the molten alloy is cooling, the temperature eventually reaches the solidification range, causing the alloy to change from solid to liquid stage. And this change of state is accompanied by a large shrinkage, which can be compensated only if we follow the proper casting techniques. Alright. So generally these are caused by incomplete feeding of the molten metal during solidification. Therefore, there must be continual feeding of the molten metal through the sprue to make up for the shrinkage of the metal volume during solidification. Occurs near the sprue casting junction. So first we'll discuss about the suckback porosity. So suckback porosity, these are often occurs at the occlusal axial line angles or the incisor axial line angles that are not rounded, and the hot spot is created, and the molten metal directly hits onto this area, and here a hot spot is created, and the metal present in this area will solidify at last, and all other area will solidify, and this area will remain hot. Alright. But actually the molten metal located away from the sprue should freeze first, and the molten alloy in the sprue and the rest of the pattern should freeze afterwards. Alright. So here as we have discussed, a hot spot is created. That is a point with higher localized mole temperature. It will freeze at last and will form Suckback porosity. So what is the remedy? The proper sprueing should be done. Using a Y-shaped sprue, the temperature of the investment under the sprue does not rise as high. Lowering the casting temperature by about 30 degrees Celsius, it will reduce the mole melt temperature difference. Next is the microporosity. So what is this microporosity? These microporosity result because of a rapid solidification of the mold or when the casting temperature is too low. Okay, it occurs from the solidification shrinkage, but is generally present in a fine grain alloy casting. When the solidification is very rapid for the microvoids to segregate into the liquid pool, and it will form a small irregular voids throughout the casting. Alright, so it is not a serious defect, but it can be detected until the casting is sectioned and can be eliminated by raising the mole melt temperature. Next is the pinhole and the gas incursion porosities. These are as a result of gases becoming trapped in the alloy during solidification. These are related to the entrapment of the gases in alloy during solidification. The pinhole porosities are caused by the release of the adsorbed gases, whereas the gas incursion porosities is caused by the release of the mechanically trapped gases. And also there is a difference in the size of these two porosity. The gas incursion porosity is somewhat larger as compared to that of the pinhole porosity. But the basic difference is that in pinhole, it is due to the absorption of the expelled gases during the solidification. What happens? Many metals like copper and silver dissolve the oxygen in liquid state, whereas the platinum and palladium have a strong affinity for hydrogen and oxygen gas. So these metals absorb these gases and they are expelled during the solidification, and they will cause pinhole porosity. Next is the gas incursion porosity. The gases mechanically trapped by the molten metal in the mold or that is incorporated during the casting procedures will form the gas incursion porosity. Generally, the poorly adjusted torch film or by using mixing or the oxidizing zone of the flame rather than the reducing zone, this will cause this type of porosity. So these can be minimized by pre-melting the alloy in the crucible former and by correctly adjusting and positioning torch flame during the melting, and obviously there should be proper melting of the mold. Next is the subsurface porosity. It occurs due to simultaneous nucleation of the solid grains of the gas bubbles at the first moment that the metal freezes at the mold wall. Means there is nucleation of the solid grains and the gas bubble beneath it trying to escape. But in the moment the gas bubble is trying to escape, in the same moment or simultaneously the metal freezes at the mold wall and they are not able to escape. So the factors responsible are the high mold melt temperature, use of short thick sprue pins. This type of porosity can be diminished by controlling the rate at which the molten metal enters the mold. Next is the entrapped air porosity or the backpressure porosity. These occur as on the inner surface of the casting and can produce a large concave depressions. Often the casting are rounded at the edges and they lack in detail. Found in a pocket at the cavity surface of a crown or MOD casting. And occasionally they are found even outside surface of the casting. This is very important to note. So what causes this entrapped air porosities? So any factor that tend to slow the venting of the gases from the mold during casting will cause the entrapped air porosity. So by using a dense investment material, obviously we are slowing down the venting of the gases from the mold during casting, and by increasing in mold density that is produced by vacuum investing, and by the tendency of the mold to clog with the residual carbon. So what are the remedies? We have to follow the proper burnout procedure, and adequate mold and casting temperature should be there. Sufficient high casting pressure should be there to escape the air, and the distance of the wax pattern from the end of the investment should be at least 6 mm. This is very important. It has to be followed. The proper liquid powder ratio can be minimized, or it has to be optimal. Next is the incomplete casting. The molten metal alloy is prevented from completely filling the mold. Obviously in that case we will not have the complete casting, and they are manifested as a rounded or incomplete margins. Often they appear shiny, and they are caused by the strong reducing atmosphere created by the carbon monoxide left by the residual wax. So what are the causes of incomplete casting? Obviously when we have incomplete burnout, high viscosity of the fused metal so that the metal do not reaches all of the intersecate areas, and obviously if we have less of the metal, when there is insufficient venting of the mold in that case also, and when there is insufficient casting pressure. So what are the proper remedies? The adequate thickness of the wax pattern should be used. The adequate venting of the mold should be there. Proper dimension of the sprue according to the casting. Optimum casting pressure, and the mold should be debris free. The temperature of the alloy should be higher than that of its liquidus temperature. So this is all about the casting defects. I hope this helps. Thank you.